Okay, welcome everyone to my fourth lecture on quantum topology without topology. So what I'm going to explain today is, well, let's start with a short recap. So we had seen this kind of two-dimensional calculus for monoidal categories, but it was a little bit biased because we were really not allowed to do kind of cups and caps, so like Morse points. And the question I would like to answer today is exactly what you can see here in this little box. So what is kind of the algebraic way to have to ensure that we have a graphical calculus with cups and caps? And the answer will be something like a pivotal category, a rigid category, or a spherical category. That's what I'm going to discuss today. These are just words for having dualities. We will see what this means. Well, in various fashions, right? So, um, yeah. So having dualities. We will see what this means. We will see a lot of examples as usual, and they will always use a certain symbol. So let me just say this, stress this right at the beginning because it's always confusing, and the literature is absolutely not consistent. Whatever. So I will use this symbol for duality, which is a little star. Um, and well, whenever I have, let's say, an object X, I will have a right dual and I will have a left dual. I should learn how to draw. I have a left dual and I have a right dual. And my convention is that the right dual has a star on its right. Okay. And the left dual has its star on it on its on the left side. Right. Here is a star for the left dual. And I should use green. Here's a star for the right dual. And again, depending on what kind of literature you like to read, this might be the opposite. It's a little bit of a mess in the literature. I mean, there are two choices, and I'm just saying right dual has star on the right, left dual has star on the left. At one point, I will get rid of the ambiguity of having left and right duals anyway. So it's not such a big deal, but anyway, just keep it in mind. Um, and yeah, this I use the symbol star for duality. Okay, and what is also important in this setup, there's a notion of taking mirrors. So instead of writing down whatever a list of 15 relations, you can write down a list of whatever 7 relations, and you say that was a bad example, but anyway, you can write down a list of certain relations, and you say all the other relations are mirrors of the one illustrated, for example. And mirror in the setup really means, well, let's say you have a diagram like this, which is a little oriented cup to the right hand side. Then mirrors include, well, mirroring around this axis, which turns the which reverses the orientation of the cup. But you can of course also mirror around this axis, which would be this diagram. So it puts the cup into the cup and also reverses the orientation, and then you can put both together and you would get whatever this diagram. So basically mirroring in this setup means just mirror your diagram as you want and allow any possible orientation. And we will see actually what these orientations mean in terms of dualities, right? So here are dualities and here are orientations, and they go hand in hand. They're basically the same thing. We will see that. Anyway, let's just jump right into it. So duality, if you remember your first class on linear algebra and you've seen the dual vector space or whatever, that's probably the first time you see kind of duality in mathematics. But duality it's just everywhere in life and everything, right? Everything kind of has a dual. You can think of yin and yang or whatever. So duality is a really, really powerful concept in the universe itself, and of course also in mathematics. And the question I would like to address today is, as I said, is kind of what is the right setup for dualities in our context of quantum topology. So what is the right setup for dualities let's say in monoidal categories. I will start with the definition. I show you some examples, the kind of the crucial examples to keep in mind, and then we'll discuss some properties. Again, the point is really duality is a ridiculously powerful concept. Okay, it's just so good. It will simplify things a lot. Um, yeah, so let's just jump right into it. So all you need is some monoidal category. Remember, this was my notation for MCAT was my notation for monoidal category. And well, as I said, there will be a right dual, there will be a left dual. Again, at one point, I will get rid of the ambiguity, and there will be just a dual. But for now, there is a right dual and a left dual. So the right dual is, as usual, I will just denote it by x star, but actually it's a triple of an object. Oh, sorry. It is the right dual of an object. Okay, so you start with x, and it is a right dual of an object. And as usual, I will set it down in a second, down later in a second. The right dual is unique up to basically isomorphism. So for now, I call it a right dual, but actually the right dual if it exists. Anyway, a right dual is a triple of x, which I denote by, well, I will denote the right dual by just by x. Say it again, x star to the right, to the upper right, right dual star to the upper right. But it actually comes with a little bit of extra data. There's an evaluation and there's a co-evaluation, which I will just draw in pictures in a second. And what is it? Well, it's just an object. Good. It's another object. Okay. And the evaluation, well, strictly speaking, the right evaluation and the right co-evaluation are certain morphisms. And well, it's always confusing which one is which because there are now 4 choices for those guys. Anyway, because we have left as well, right? So it's evaluation, co-evaluation, 2, and left and right. I got another 2. So there are 4 natural morphisms you can kind of draw. And well, whatever. And let's hope I got this correct and everything is consistent. It's always a bit confusing. It doesn't matter. The idea is as follows: you can tensor your x, you can tensor your object x with x dual. Oh, I said I call it star, whatever. So a little star. This is not a star. Anyway, little star, and evaluation now will be a morphism to that entity. Okay, and the co-evaluation is the other way around, and you will see some examples later on why I want to call them evaluation. Co-evaluation. The only tricky point is that you want to compose them in a certain way. So if the evaluation goes from, let's say, maybe I do the star in a different color. Let's say it goes from x star to 1. Then the co-evaluation better goes from x star x, from 1 to x star x. And you will see in a second why I want this to be this way. So whatever those co-evaluations are, they are morphisms from x. Put your dual object somewhere to x. Put your dual symbol somewhere, but now on the other side. And I will draw those little pictures because I never can remember how the abstract definition looks like. So this is my co-evaluation evaluation picture. It has an x input, an x star input, and it goes to the identity, and the identity is omitted. So it goes to nothing, and I just put a box, which I labeled by, well, evaluation. Similarly, my co-evaluation is, again, just a box. Now it starts at the identity, and it goes to, remember, this is kind of the opposite here. The dual is to the right, and here is the dual. At one point, the dual is to the right, and at one point, the dual is on the left-hand side. And I want this to be this way because I want to compose them in the following way. I want to put evaluation here. I want to put the co-evaluation here. And something is wrong with my drawing today. I want to put the co-evaluation here. And I want to connect them along their one common, so they have one common input, x dual here. So this is a dual input, as you can see it here. And this gives me a morphism from X to X, which I will illustrate in the following way. Well, so it goes from X into co-evaluation and goes back to X. Okay. And I can do it the other way around, and that's why I want to have it in a certain way. I can do it this way, and I can go in here. This was a bad picture anyway. I can go in here, and now they connect via X, and it's a morphism from X dual to X dual, from X dual to X dual. Okay, it's a morphism from X dual to X dual. And the whole point is that this morphism is non-degenerate. That's the word, non-degenerate in the following sense. Well, it's a morphism from X to X. Do we know any other morphism from X to X? Yes, we do. We know the identity morphism from X to X. So composition of evaluation and co-evaluation is the identity in both possible ways of composing them. All right. So in a slightly less rigid version of drawing it, I basically have said that I have a composition like this, which is this, and it goes from X to X. And I have it the other way around, going from X dual to X dual. Yeah, you will see in a second what I mean by those diagrams. So you have something from X dual. Ooh, this was bad. You have something from X dual to X dual. Anyway, yes, so two morphisms, and they compose in two ways, and both compositions are the identities. That's what we call a non-degenerate. Okay, so a dual is basically something that you now have an operation, evaluation and co-evaluation, and they are reversible in a nice sense. Like if you do co-evaluation and then evaluation, you can pull it straight, or if you do it the other way around, you can also pull it straight. Right, like a zigzag, and you pull it straight. And yes, and we will make this much more precise and much nicer later on in a second when we kind of ignore the difference between left and right. Because, of course, we also have a left dual, which is exactly the same definition, kind of just the other way around. Namely, yeah, I mean, all your pictures are kind of reversed. So X dual goes to evaluation, X dual X goes to evaluation, which is now kind of the left version, and there's a right version as well. And there's a co-evaluation version as well. And the way I distinguish them in the notation is a bit tricky because in the end, I don't really care. In the end, I want to get rid of left and right ambiguity. But anyway, so the right ones will have the X in the subscript, and the left ones will have the X in the superscript. So here. And as I said, the left dual is on the left and the right dual is on the right. And the non-degeneracy condition is exactly the same, but now in the opposite order of composition, right? Because now you can compose in the opposite direction. And I really would like to, and I will call those two relations the zigzag relations, okay? This was bad. Try again. I call them the zigzag relations for a reason we will see later. Well, when I get rid, as I said, of the ambiguity of left and right. Yes. So here I say really is a left dual, and I say it's a right dual. But this is kind of unnecessary because you have the following lemma. If they exist, and this is really the crucial thing, they might not exist, okay? But if they exist, they're unique up to unique isomorphism. So as unique as they could be, which just means I kind of want to they're the right dual and they're the left dual, right? Not a, but the left dual and the left right dual. And it's not hard to see. I mean, yes, if you have two different maps, then you can basically use the zigzag relation to construct to construct the isomorphism. If you have two different duals, which I call overline dual, right? So the zigzag relation kind of works like this. The overline dual, you do the overline evaluation, and you can compose it um, with a co-evaluation for x, and you do it the other way around. And if you compose them, what you will see in the middle is here, like let's say you stack it like this, then it looks like this. Okay. So let me see. Here's evaluation bar. Oh, sorry. This was a bad illustration. Here's evaluation bar. Nah, my mouse doesn't work today. Evaluation bar. Here's co-evaluation bar. Here's evaluation. Here's co-evaluation. And then you can pull these guys straight. And then you can pull the other guys straight. So this completely pulls straight. So that's why they're inverse. Yes. Okay. So it's really an easy argument if you think of those as kind of zigzag relations. You stack them together twice, and in the middle you will always see one of the so evaluation and co-evaluation meet, and you can always pull them straight. That's a non-degeneracy condition. And then you will see co-evaluation bar and co-evaluation bar. They meet, and so you pull it straight. Do it the other way around. First evaluation bar and co-evaluation bar meet, you pull them straight, and so on. So it's actually a very easy argument. It's basically, yes. So that's why I want to call it zigzag relation, because this and many arguments like this is basically you have a string which goes zigzag and you pull it straight, right? Zigzag and you pull it straight. And that's basically it. That basically is the whole concept of duality in monoidal categories. You have zigzag and you pull it straight. And yeah, I mean, there's some funny facts about that you just prove. Like if you first see a definition of a group, you will prove some trivial facts like the inverse is unique and whatever the neutral element is unique, something like that, and you prove something like this. Some very easy consequences, in which hold in any category with duality, basically. So first of all, self-dual just means an object is isomorphic to its duals, and the monoidal unit is always self-dual. Right? Left and right doesn't matter. Monoidal unit is always self-dual. But basically you can take the unit as co-evaluation morphisms. That's basically the proof. And this, by the way, implies that the monoidal unit always has a left and a right dual, which is well, it's a true fact, right? You don't need to. Just in any monoidal category, you have a left and right dual of the monoidal unit, which is the monoidal unit itself. Second statement, if X has a right and a left dual, then the right and left dual are actually inverse operations. So this is kind of a nice fact. So the left dual of the right dual is the right dual of the left dual is the object where you started with. And the isomorphisms are those. basically. So I leave it to you to write it down, but it's a zigzag argument. Yeah, and of course, kind of left and right dual are related by some kind of turning structures from left to right. So if X has a right dual, then in the corresponding co-category, X is a left dual, and vice versa. So they're really dual concepts, as you would expect, right? It's a left-right symmetry. And indeed, that's what I will call it. I call it a left-right symmetry. Basically, it says every statement about right duals is a left counterpart and vice versa. So in some sense, you only need to write down statements about right duals or left duals, whatever you prefer. So this is kind of a crucial thing. It's easy to observe, but it's kind of crucial to keep in mind. Every statement, so there's a left and right symmetry. Every statement has some equivalent statement on the left-hand side. Every right statement has some equivalent statement on the left-hand side, and vice versa. Okay, so before I go to examples, let me recall what we did. Well, I discussed this concept of a right dual and a left dual, which are actually the right dual and the left dual if they exist. And it's basically an object together with a zigzag morphism. That's basically what it is. Or with two cap and cap morphisms such that you have a zigzag relation, which I call the non-degeneracy condition. And now in the examples, you will see why I would call this a non-degeneracy condition. So the first example of duals. And okay, the first example is a bit of fancy example. The second one is actually better. So, but anyway, let's do it. In any monoidal category, in the monoidal category of endofunctors of a category, it was a monoidal category, remember, left duals and right duals correspond exactly to right adjoint and left adjoint functors. So if you don't know what right adjoint and left adjoint functors are, then they are the definitions from above, left and right and left dual, whatever, in this category of monoidal or endofunctors of C. So the above is basically a new interpretation of adjoint functors. Adjoint functors is something I haven't talked about much, or almost not until this point, but they are a very classical concept in category theory and a very powerful concept. Why? Well, because they come actually from duality. It's kind of a dual functor. And well, it is a dual functor in this sense, right? That's what the example is saying. But let's do a hands-on example, a down-to-earth example, right? So what is the easiest category I can imagine? Well, something like vector spaces over some field. But not really every object has a dual. And you should know this from linear algebra, right? When you remember your first, second, whatever class on linear algebra, you might recall that duality is a very powerful concept in vector spaces, but it usually always fails for infinite dimensional vector spaces. Actually, in this case, you could show that an object in vector K has duals. So left and right dual will be the same here in anyway. So has duals if and only if it's finite dimensional. And for finite, I'm not stating that. That's a little bit of a painful proof, but it's not hard, but painful. But let's just see one direction, namely if X is finite dimensional, then I claim that that X actually is X dual, is actually isomorphic to X dual. But anyway, let's just ignore that. Let's just strictify that it is X dual. And the co-evaluation and the evaluation maps are ones you think you would use, namely exactly the ones you know from linear algebra. You just choose two bases. It's very easy. x1 up to xn, and the dual basis x1 star up to xn. And of course, these are bases of x. Oh, this was the wrong one. Of x star and green x. And the co-evaluation is the co-pairing. It's in abstract figures, it's just this one. And the evaluation is easy map. It just evaluates. Uh, uh, so x dual is of course a linear function on x, and it just y dual is a linear function on x, and it's just evaluation. And everything is built such that, well, it's non-degenerate because you have dual bases. And this was one of the classical theorems you see in linear algebra, like the dual space is actually isomorphic um, to but both of them are, by the way, isomorphic to X itself. But anyway, yeah. So the dual space is isomorphic to X itself. They have the same. They have a basis in the dual basis, and co-evaluation maps basically give you the isomorphism. Okay, this is kind of the classical example. Duality in vector spaces is what you think it is. It's linear. You go to the linear function setup of the dual vector space, and you have very natural pairing and co-pairing maps, evaluation and co-evaluation maps on that vector space. And the only thing you need to basically do is to write them down, is kind of to choose a basis in the dual basis. And this is exactly the concept from linear algebra that you've seen before. Yes, so this is a nice example. It's an example to keep in mind. This is a nice example. And here's a diagrammatic example. It's another nice one. This is also a nice example, but it's a little bit of a fancy example. Here's another nice example. Something you should really keep in mind, because those two are basically the two prototypical examples. So most diagram categories which you've seen have duals. And the duals are exactly the maps you think they should be, and they're the maps diagrammatically of how I would like you to think about duals. Namely, remember the temporal leap or the Brouwer, whatever it was this diagram calculus. So Brouwer was the one where you had crossings, cups and gaps and whatever. And you had one generating object, which I called bullet, which is just what you put at the bottom and at the top. Let me see, here's one. Here's one, and here's one. It was just this bullet object, and it's self-dual in this sense. Remember, this was self-duality, so left is right is the object itself. And how do you see it? Well, what are the evaluation maps? What are the co-evaluation maps? Well, this is the evaluation map, and this is a co-evaluation map. And how can you see this? Well, you would need to check whether they are degenerate or not, and this is basically this diagram. Well, whatever. So whenever you see a cup and a cap, then you can pull it straight. What was that? Then you can pull it straight. Okay. That's basically what it means to be an evaluation and co-evaluation and non-degenerate. And that's kind of, again, the picture you should keep in mind. Evaluation, co-evaluation, those are basically cup and cap maps in some abstract setup. And this is how I drew them before, right? I just put a box, but you can imagine that, well, this was right. I just put a box, but you can imagine that there is actually a cup sitting here, right? Not quite because of the stupid left and right thing, but we will get rid of left and right ambiguity in a second. Not really get rid of it, but you will see. I really want you to like to think about left and right duals as being left and right evaluations and cover evaluations, whether left or right. I want you to think of them as being gaps and gaps. And the non-degeneracy condition is a zigzag, meaning you have a piece of string and you just pull it straight by just grabbing it on both ends and just pull. Yeah, and okay, then in this oriented Brouwer category, it was a self-dual because we had orientations, right? So yeah, something like this. But at least left and right dual are the same. So I forgot my conventions, but let's say it was this way. So it's not self-dual, but left and right dualities are the same, but you still have dualities, and they still look like cups and caps. And again, I said again, this is kind of the diagrammatic incarnation of duality, and it's a good prototypical example of a diagrammatic incarnation of nullity. Okay. And also, it's a bit tricky. Of course, there's my other favorite example. It's those group-graded vector spaces, which you can potentially twist. Remember that you can potentially twist them by a co-cycle, which is this omega. And what I will say here, and what I'm explaining in this example is that duals are unique, but evaluation, co-evaluations maps are not unique. Remember that with a monoidal category, actually the monoidal structure was a choice, and we're kind of always suppressing it. It will be the same here. There's a choice involved, and I will kind of suppress it, but you should keep in mind that there's actually a source. So let's look at the example here. So basically, you can scale evaluations and co-evaluation maps by scalars. So think of it, if you put if you want something like a zigzag relation, and you decide to scale both this one and this one with a -1. So you know that, let's say you know that it holds, and you scale both with a -1. And it still holds, right? -1 times -1 constant, so it still holds. So you kind of have a choice of scaling those maps, and sometimes it matters, and different choices give you, strictly speaking, different, what we will call in a second, rigid structures. So let me run through this example. It's very easy. Like those group graded vector spaces are always very easy. Remember, this in this case, Emo2. It's just a category with two objects, trivial home spaces, and that's basically it. And the multiplication rule is the multiplication rule in the group. So as a graph, it's just two objects with maybe some identity morphisms here. And I really love this example. It's always very easy and silly, and still tells you a lot of it's very easy but not silly. It still tells you a lot about the underlying theory. Okay, so this category has only two objects, which I call 0 and 1. I mean 0 mod 2. So here's my object 0, here's my object 1. And the monoidal product is exactly the addition of numbers in Z mod 2. So, and this is a monoidal unit. 0 is a monoidal unit, so we already know 0 is self-dual, and 1 is also self-dual. And since 1, it's a little bit of a silly notation, but 1 plus 1 is 0, so you know that left dual, you know those two equations. Okay. And yeah, the monoidal unit has basically one choice of evaluation, co-evaluation maps. But the object 1 has several, admits, okay, the object 1 admits several co-evaluation maps, which we will see now in action. And yes, and I just do it for the right duality, but of course there's similar for the left duality. What you basically do is, right, so you do the following. Let me see. You do this picture. Okay, this is this map. Maybe I should have used whatever. All right, this is this map. Let me do it this way. Okay, this is this map, and then there is whatever, a green map the other way around, and it's of course this map. Fantastic. And because this was this kind of funny category where everything was twisted, and if you write it down in the strict setup, you will see there's a bracketing isomorphism here in between. a bracket isomorphism. So kind of you have a choice of bracket here. And what you need to put here is the associator, alpha. And alpha actually is a sign in this case. Okay, alpha puts a sign. Um, all right, and this should pull straight, and alpha puts a sign. So this should be whatever. Let's do it. This should be this morphism, and alpha puts a sign. So whatever kind of scalar you want to multiply evaluation by, which is this map, you need to scale co-evaluation by the inverse of the scalar with a minus sign in order to get this equality, because alpha basically is a minus one, right? It's a multiplication by minus one morphism. And if you would do the same for the object 0, then you would realize, oh, then you can only scale by A and A inverse. So you have kind of a creepy minus sign coming in here from the co-evaluation. So all this example is saying is that you have to a little bit be careful with what actually your duality maps are. So again, as I said, I usually like to kind of sweep this under the rug, like duality is duals are unique, but duality maps are usually not unique. Just keep that in mind. Okay, and yeah, so the definition. Well, we do category theory in some sense, right? So if duality should be something that exists for morphisms as well, and yeah, you can write down the left and the right, this is the right, and the left so-called mate of a morphism. So if you have a morphism f from x to y, you get a morphism in the opposite direction by using, let me see, those two pictures and the blue one. So let me try to explain the blue one. So f sits here in the middle. It's a morphism from x to y, and you can compose it with the evaluation or with the co-evaluation to get a morphism from a y dual to x dual. Another way of illustrating this is if you have f a little bit of easier fashion. If you have f sitting in the middle, you get its mate by doing an operation like this, and it turns the order around. So if this is x and this is y, you now got a morphism from y to x. So strictly speaking, from something like what is it, y left dual, from y left dual to x left dual. Right? And they satisfy exactly what you think they satisfy, because you turn the order around. If you do it, you turn the order around after composition, and that's an exercise. And yeah, you just draw the pictures, you will see it. And the same happens for on the object level. So always be careful. Dualities turn to things in the opposite direction, right? This kind of swap order. So x tensor y dual is y dual tensor x dual, and the other way around. Okay. And why do I say this? Well, because there's the first important theorem which makes duality so amazing, and this is easy. I mean, the proof is playing with those diagrams, right? This is the proof. And you use a dual diagram, you compose everything accordingly with evaluations, with evaluations and co-evaluations in the right way, and use the zigzag relations. So the proof is easy, but the observation and the theorem itself is so amazing. So if you want to compute Hom spaces in a category with duals, you can always pull duals to the other side. They're all the same. They're four versions of the same thing. So let's look at the blue one. So Hom from x to y, Hom x, y to z is the same as you can pull x to the other side. Okay, I've pulled x from here to here, and the only thing I need to do is I put the dual in the right place, right? So I can pull things from one side to the other by using duals, and this is really an important theorem. It's really good. It's really good to keep in mind. Proof is, as I said, basically trivial or easy. Well, maybe not trivial, but it's easy. Okay, yeah, I mean, this is a really good thing, and we will see it several times. So just keep it in mind. Basically, so let me say it again. Basically, you can use dualities to pull objects in homes from one side to the other. Right? You just have to be careful where to put your. And I never remember how this works. That's why I write it down. Um, so you have to be careful where to put your duals, and in what sense. So like if you have, I've always want to pull x, and if x is here, then you can pull it to here with a right dual. But if it's here, then you have to pull it here with a left dual, for instance. I never really remember how that works, so that's why I wrote it down. But basically, you can pull it from left to right. That's what you need to remember, and from right to left, of course, by duality. That's a cool thing about duality. So this is really one of the most important features of duality. You can massage your home spaces to make them easier. Maybe one of them is easier than the other. For instance, a really good one is usually, hoping that I get this correct now, for xy is actually then isomorphic to home, let's say, uh, from the monoidal unit. So I want to pull x to the other side. I just have to be careful where I put it. Let's say it's x dual y. Right. And so in some sense, in the monoidal category, it suffices, in the category with duals, it suffices to know home spaces from the identity to basically any object. And that's usually what people study under the umbrella term of invariant theory of invariance, like how often does the unit appear in a certain composition of objects. All right. I'm running really badly on time, so let me just skip over this. This basically is, well, that duals behave nice under monoidal functors. So if x is a right dual, then f of x is a right dual of, so x is a right dual of x, and f on x is a right dual of x dual is a right dual of x, so f of x dual is a right dual of f of x. And the only thing you need to assume for that is that f is a monoidal functor. This is kind of a little bit of a surprising thing, but it's not so hard to see. So if you have a monoidal functors preserve dualities. It's not a very complicated calculation. And this motivates, well, all the story above up to this point basically wants to say dualities are cool. That's basically what it wants to say. They like zigzag relations. They are like relations like this one. They're like cups and caps. They have this really good theorem of pulling objects from one side to the other in home spaces. So maybe it makes sense to kind of formalize this in some category terminology, like come up with some terminology. And what people usually say, it's the category is rigid if, well, what was the only drawback in this whole discussion? If duals exist, they're unique. Okay, there was a slight thing with, okay, left and right dualities might not be unique, but let's ignore that for a while. If duals exist, they're unique, but in vect, for example, not every object has duals. So duals might not exist, right? So, and now you just say a category is rigid if every object has a right and a left dual. Okay. So now a rigid category is basically you do not have to worry about existence of left and rights anymore, duals anymore. They exist by definition. Finite dimensional vector spaces are rigid. That's what I did above, right? In this example, vector space is not rigid, right? An infinite dimensional vector space doesn't have a dual. Basically, all the diagrammatic categories we have seen are rigid. So Temple and Liebenbauer in their oriented versions, whatever. Not the symmetric group picture, because in this, remember in the symmetric group picture, which basically had diagram, or well, it was a symmetric group, so I shouldn't draw crossings. It basically had diagrams like this, whatever. You were not allowed to do cups and caps, so no cups and caps, so this is not rigid. But everything that basically has caps and caps in the diagrammatic calculus is rigid. Like Bauer. And of course my my favorite toy example, like G-graded vector spaces. And the dual is always the inverse. Which in my Z2 example is a bit boring because everything is kind of self-inverse. But in general, the dual is inverse in G-graded vector space. And how can you see this? Well, you always have a map in G-graded vector spaces by G inverse to the unit. And that's basically your evaluation map. And you have so this is evaluation. And there's a map the other way around, which is, of course, the co-evaluation. Oh, shit. Cool. And that's why you need the dual. Man, the dual is the dual. Sorry, that's why you need the inverse. The inverse is the dual. Okay, and something funny, something a little bit tricky. So, of course, if you have duality, and you can take the double dual, the dual of the dual, and I will denote it by this, and it's really just the dual of the dual. And there's a left version, and there's a right version, and there's a left version. And if you remember why I'm only doing it in this way and not in all four possible ways, because we have seen this one. So today my drawing is really bad. We have seen this one. So two of the four possibilities to put a double dual actually collapse, and they're the identity. The other ones don't need to be, and that's why I have those two notations for the double dual. Of course, then you can take triple duals and whatever. But the double duals are a little bit interesting. Something is wrong with my... because there's something funny. As soon as you have this one, as in all the examples I've showed you so far, so if left and right are the same, then actually double duals are the identity. Why? Because you always have, let's say, right, left is the identity. So if left and right are the same, then the double duals are always identities. But in general, this is actually not true. So in general, this is wrong. Okay, so in general, this is also wrong. Double duals don't need to be isomorphic to where you started, which is a little bit tricky because it's not so easy to construct examples. Right? In all examples we have seen so far, the double dual is the object you started with is the identity, but in general, it's not the case. And yeah, it's not easy to construct example where this really fails. But keep it in mind, it does fail. It's not, right, not always x double dual is x. almost always, if you want, because in almost all examples that you will ever see in nature, it will be, but not always. I won't go too much into details because to construct examples of where x double do is not equal to x, it's not so easy. It's not super hard, but it will kind of uh, get me too far away from what I really want to say. Just keep in mind that it doesn't come for free. Yeah, and the funny thing is, I mean, let me say it again. Here in this proposition, basically, uh, monoidal functors preserve dualities. So what I should do is, what I usually do is like I have a new notion, so I have a new notion of categories, so I should have a new notion of functors. But we already know that kind of monoidal functors are the correct definition in the monoidal category, so we kind of automatically get this category of rigid categories, which are called R-cut. And but by mirroring, you will see this is kind of almost a trivial statement. So if you have a rigid category, so you have right and left duals, then the opposite, the co-category and the co-opposite category are also rigid. Just mirror your diagrams in the appropriate way. Anyway, and kind of the statement you want to come up next. You want to make next is kind of the dualities are functors between those categories. Okay, you can define a right dual functor. Right, I told you what duality is doing on objects. I told you what duality is doing on morphisms. So the left and right mates from above. Remember that was this picture. Or the other way around. So you certainly have dual functors, but because they turn everything around, they actually, it's a bit, well, they go from C to C co-op, so they turn everything around. But what they basically do, not so important, what they basically do is they send an object to its dual and a morphism to its dual, either left or right, and they are actually equivalences of monoidal categories. So they identify C with C co-op from left and right. Yeah. And of course, depending on how you want to state it, they would also identify C op with C co, depending on how you want to state it. Anyway. And because of this, and because of this mixture between left and right duals, you get a statement about double duals being isomorphisms. Right? This is not saying that the double dual, so the double dual doesn't need to be X, but it's still an invertible operation. And you can invert it by, those two functions invert themselves, basically. Right? So this is the inverse of this one. And the nice thing about taking double duals is now that you get the corresponding statement from C to C and not from something like C to C co-op. And you can state them in various versions, as I say here. So they give you really equivalences between all those, well, whatever you like. I mean, this is just a choice, right? Whether you like C or C op, this is really just a choice. Okay, there's also a statement on the Grothendieck ring, which I won't go too much into details, but basically, if you have a duality upstairs, you have a duality downstairs. You have pairing type of morphism downstairs. Yes. Okay. And okay, even though a monoidal functor preserves dualities, a monoidal functor does not necessarily need to preserve evaluations and co-evaluations. Remember, there was a choice involved. And you would just call a monoidal functor rigid if it does. So it's between two rigid categories, and you have some dualities, and it sends the duality on one side to it sends the evaluation on one side to the evaluation on the other side. Same with the co-evaluations, and either left or right. And so, in the usual sense, compositions of rigid functors are rigid as usual. I mean, this is usually how it builds, right? The identity functor is rigid. So you get a category of rigid functors, which I denote by hom star in contrast to hom monoidal. And it's a subcategory of monoidal functors between rigid categories. And you really want to say that two categories are equivalent as rigid categories if there is a rigid functor between them. So you more than just keeping track of objects and duality on objects, you want to keep track of duality on morphisms as well. And exactly why you do it is because there is some choice involved regarding the evaluation and co-evaluation maps. Okay. So far so good. So let me recall. So basically what we have seen so far is the concept of duality. The concept of duality is really powerful. It comes from duality on vector spaces. I like to draw this diagram several times. It's basically this one. You need to remember, or some kind of mirror version of it, of course. It naturally leads to the definition of a rigid category, which is a category where everything has left and right duals. Classical examples are finite dimensional vector spaces, finite dimensional vector spaces, right? Not all vector spaces, finite dimensional vector spaces, and basically any kind of diagrammatic category you can imagine. Yeah, and it has a nice diagrammatic calculus, which I will go into some more details later because it's slightly flawed at the moment. There's this left and right dual thing, which is a little bit annoying. You really never really remember which is left and which is right. And in almost all examples, it doesn't matter, like in vector spaces or in those Brouwer categories. Right? It doesn't really matter which is left or which, and also in this G-graded vector spaces, it doesn't really matter. So we want to get rid of this, and this is what I'm going to do next. But there's a short interlude on categorical groups. It will be pretty short, but it's actually nice. So let's do it, and then I will get rid of the ambiguity or the choice or whatever you want to call it of left and right duality. And in some sense, this duality wants to tell you that the corresponding categories behave a little bit like groups, because every object has kind of an inverse, right? Every object has an inverse, an X and an X dual, and you have a morphism to the identity. It's not quite an inverse, because this relation here tells you that they're kind of invertible, but strictly speaking, they're not invertible, right? They're just kind of invertible. They're reversible operations, but they're not invertible morphisms. And you just say, well, okay, then I will just call an object in my category invertible if evaluation and co-evaluations are actually isomorphisms. So they're not just reversible by zigzag relations, by non-degeneracy, but they're really isomorphisms on the curves. Okay, and this is kind of what you call a categorical group. But if every object is invertible, you would call it a categorical group. Because, well, of course, you have the standard things you could draw about these, like, okay, this might not be completely standard, but in this setup, if you have a left dual and a right dual, then they are the same for invertible objects. And of course, the inverse of an invertible object, right? The inverse in this case is a dual, so the inverse is invertible, and compositions are invertible. So, like, as you would as we would have it for a group, right? And the proofs are just, you can look at it in my lecture notes, which of course are linked downstairs. Um, and the proof is basically trivial. Um, and all this lemma is saying that in any monoidal category, you get actually a monoidal subcategory inf C, uh, and the group, and that's why it's called group, namely uh, so which are also called inf C, which is just K0 of the invertible objects. So one of them is a category, a group-like category, a monoidal category, and the other one is a group. Why is this actually now a group? Well, um, because those are isomorphisms, so X dual in the group really is X inverse. Right? And well, the terminology is then kind of pretty straightforward. It's a categorical group if so. This always exists, and it's a categorical group if the invertible objects are just everything. Um, and it's what you think it is. Like what are the invertible objects of vector spaces? Well, if you have a 5-dimensional vector space, then whatever you tensor to it, you will at least have dimension 5. It just can get bigger. So the only invertible, and you would need an isomorphism to a 1-dimensional vector space because the monoidal unit here is K. So the invertible objects is just 1. And this is exactly what you think it should be, because in K0, the only invertible object in this monoid is, of course, 1. So the only invertible object in finite dimensional vector space is the ground ring itself. Similar for the Brouwer category, there's not, or kind of any of those diagrammatic categories, there are not many invertible objects. But of course, in our good old friends like G-graded vector spaces, I mean, G-graded vector space is a categorical group, right? This is how it's built. The dual is inverse anyway. And this whole setup of categorical groups is kind of a generalization of this example. Right? That's how you should think about it. Okay. This was just a short interlude. Categorical groups generalize. It's really not so long. Categorical groups generalize these G-graded vector spaces. There's a certain subcategory of invertible objects, and if all invertible objects, if all objects are invertible, you have a categorical group. Okay, but this was just a short interlude. It's nice to read. It's nice to know. You can play around with it a little bit more, but my real goal is to get rid of left and right nonsense, and that's what I want to finish with. So, and this is called pivotality. So pivotality is just the observation. Well, almost always left and right dual agree. So it was here. In all of our examples, left and right, in all of our examples we have in mind, in almost all examples you ever write down, left and right duals are actually the same. And it's kind of a pain to keep it around. So come up with a definition that you will then use all the time, where left and right dual are the same. And this is exactly this definition of pivotality. Pivotal is just a little bit stronger than left and right duals agree. You say the left and right dual, the functors of left and right dual are isomorphic. It's a stronger statement than left and right duals agree. Right? It's also saying something about morphisms. And so then I call this category pivotal. Right? The functors are isomorphic. And again, the literature is a little bit of a mess with respect to pivotal structures, because what you can with respect to pivotality, because what you can also call pivotal would be a certain choice of isomorphism between those functors. And I will call this a pivotal structure. So pivotal structures are not, whether a category is pivotal is a yes or no question. Pivotal structures, on the other hand, are choices. So there's a choice involved. And again, I say it again, be careful with the literature. Some people, some authors call a category with the choice of a pivotal structure pivotal, and whatever. In my notation, pivotal is the one which you can answer, which you can click a box like yes, it is pivotal, or no, it is not pivotal, because it's a statement about dualities, about whether two factors are equivalent or not. And the pivotal structure is a choice of an isomorphism. And the thing is this very easy proposition that in a pivotal structure, double duals are identities. In a pivotal category, double duals are identities, or even stronger, the double dual functors are identity functors, or isomorphic to identity functors. And of course, this implies that, I mean, if the double dual functor is the identity, this definitely implies that it acts as a morphic to the identity. If left dual functor is equivalent to right dual functor, this certainly applies that left dual is equivalent to right dual. So my assumption is on pivotality is stronger than what I really have in mind, and what I really have in mind is left and right duals are equivalent. And I say it again, why I want to do this, because we're doing category theory, right? I should say something about functors and morphisms and not about objects. Also, in the end, my mind at least thinks about objects. I shouldn't do that. So pivotal means that functors are equivalent, but it's completely fair to just, okay, objects are equivalent as a consequence. So why not think about it until you really need to worry about morphisms? Just think about pivotal means left and right duals are the same for objects. It's a stronger statement, so you're kind of fine, but it's good to remember that pivotal just kind of wants to mean left and right duals are the same. Strictly speaking, they're the same up to isomorphism, because we're doing category theory, of course. Yes, and all the examples we kind of care of, Brouwer, graded vector spaces, finite dimensional vector spaces, are pivotal categories. And the classical duality would be a pivotal structure, for instance, for finite dimensional vector spaces. Here the pivotal structure would be the identity, and here the pivotal structure is, well, what do you think it is? What do you think it is? Okay. Right. So all of our favorite examples are pivotal. All right. And the one with the W here is also pivotal, but maybe then it's a bit trickier to talk about a pivotal structure. That's why I omitted it from this example. But anyway, let me just point out the difference of being free again. The free rigid category, like remember from last time, free monodal category, generated by one object is not pivotal. It would be one of those examples where, well, this one, where you can take arbitrary powers of arbitrary duality. So like bullet dual is not bullet. Bullet dual is not bullet. Bullet dual is not bullet, and so on. So it's really free. So you can take the fifth hundred dual, and it's still not dualities of infinite order. To show that is a little bit of a pain, but it would be. The free pivotal category generated by one object is actually the oriented temporal leap category. Why? Well, you have one object, and it's free pivotal, so you only have to worry about having it a dual. And the only morphisms you need in this free category, by definition, are the corresponding evaluation map satisfying the corresponding zigzag relations. And that's exactly the oriented temporal leap category. Right? It's the oriented one because I haven't enforced any relation on duals, on self-duality. If I would say the free pivotal category generated by one self-dual object, then I would get my TL category, because the only thing I would need is a cap and a cap morphism, and they need to satisfy the corresponding zigzag relations, right? Remember, free means only impose the relations you really need, and those are really two good examples. Free pivotal is the oriented temporally, but free pivotal with one self-dual object is a temporally. Yeah, and of course you get then the category of pivotal categories. But the only thing that makes sense here is that, well, the category of pivotal categories, where the objects are pivotal categories, but the morphisms are rigid functors, because those were the functors that keep track of dualities. That's what you should do for a pivotal category. Here's a funny lemma you should try yourself. In a pivotal category, left and right duals are conjugate to one another, which basically means they're the same. Not quite there as conjugate, but basically left and right duality says that objects are isomorphic and morphisms, the dual morphisms are conjugate. So I kind of can ignore the difference between left and right, and even more, I really can ignore it in the following sense. I would call a pivotal category strict if dualities are not isomorphic as functors, but if they are on the nose equal as functors, then I would call it strict. And in this case, there is no conjugation anymore, and everything is just strict on the nose. Left and right mates are the same. I don't need to write. I don't need to distinguish this and this anymore. They're just the same. So I always write duality on. In this case, I always write my dualities on the right. So I always use the right dualities, because it's equal, and I kind of need to make a decision. And I like this one. So this one is a good one. Well, it's the same, right? It's not a good one, but I like it more than the other. So in this strict setup, and not quite trivial theorem, but kind of well known, says that remember, in the strictification theorem for monoidal categories, every monoidal category is equivalent to a strict monoidal category. And the same is true here. Every pivotal category is equivalent to a strict pivotal category in the pivotal sense, right? So in the dual sense, in the star sense. So in the sense you want it to be. This is not the theorem is not hard. It's not hard, but it's too annoying to state it to prove it. So I just omit the proof. The point is, of course, the same as for monoidal categories. For strict pivotal categories, I have a nice diagram calculus, and in some sense, I can strictify all pivotal categories. So I always have a diagram calculus for my pivotal categories, and that's basically the last thing I want to do. Not quite, but well, we'll see. But it will be very nice. So in a strict pivotal category, and this theorem tells you that all categories are strict in a reasonable sense. I will draw the following pictures. I have identities on X, and I will draw identities on X as a string pointing upwards. I have identities on X dual, and I will draw them as a string labeled X now, pointing downwards. So X dual is the one pointing downwards. Keep in mind, we're in a pivotal setup, so no distinction between left and right dual. So I can just say the dual points downwards and the original object points upwards. And this gives me now what I wanted to do from the very beginning, right? I wanted to have those co-evaluation maps, and I have 4 choices for them, like X goes to X dual, whoop, or X goes to X dual in the other direction, or just all 4 possible ways. And they satisfy what they should satisfy. Finally, in this strict pivotal setup, I can really strictly speak. I can finally draw those diagrams I always drew the whole for this whole lecture, right? This is what I want to have in mind. For a rigid category, I would draw this funny strictly speaking, should draw those funny box-like pictures, but this is what I have in mind. And in a pivotal category, it works. I can just draw my zigzag pictures, and it's just an oriented string, and you pull it straight, and it does exactly what you think it does. And kind of what you have is that these are invertible operations. They're not isomorphisms. That was a categorical group thing, but they're invertible operations. And this is really good. So whatever you do, you can just whatever you do in some sense, you can just pull caps and caps. You could pull your diagram in a different position, and whatever kind of argument you have in mind, it still holds for the let's say rearranged diagram that you have pulled into another position. For example, in this category, we would have an equation which looks like this. So pulling things to the right and pulling things to the left is the same. So whether I do this one with my box here, or whether I do this one with my box here, they're just equal. And so left and right duals, left and right mates are equal. That's basically what it is. So you can kind of think of, you slide this box around, pull it straight, then you're done. And you can do the same here. You slide this box around, maybe with a different color. You slide this box around and pull it straight. And then they are the same. And this holds in any strict pivotal category, but as I said, in a reasonable sense, all pivotal categories are strict. So it gets this nice diagrammatic calculus. Here's another one, which I call the sliding operation, which I secretly just did here. So the order of the lemma is a little bit arbitrary. Lemmas is a little bit arbitrary, but anyway. So if you slide a morphism across a cup, then you just get the dual morphism. Oh, this was really bad. Then you just get the dual morphism. Okay, so sliding morphisms around cups gives you the dual morphism. And of course, you all have all four possibilities of doing this. So you have all mirrors. And this is an operation I call sliding. So coupons slide around cups. So you have a sliding operation. Coupon here potentially with a duality. Yeah. Sliding. So maybe you can already see it, but those categories are really built to have a diagram, really like a honestly topological diagrammatic interpretation, right? Like now you have your coupons everywhere, you have your diagrams, which might look like crazy things, and you can slide everything from left to right, and it's really beautiful. And the proofs are easy. So please have a look at the proofs because they're really cute and easy, but I'm running out of time. I mean, pictures, just look at the pictures. Pictures will tell you everything. Because of time reasons, I will not go into details, but there's a canonical choice of pivotal structure. Whatever. Please have a look in the write-up, but remember that pivotal and pivotal structure is not quite the same, but there's kind of a canonical choice of a pivotal structure which has some nice properties. It's this diagram, and whenever I say something is a pivotal structure, I usually like to use the canonical choice. On vector spaces, it's exactly what you think it is. It's a canonical isomorphism or basically the canonical isomorphism from X to X dual. From X to X double dual. That's where it goes. It's a diagrammatic version, if you want, of the canonical isomorphism in vector spaces from X to X double dual. Anyway, and yes, so here's actually the example. The example tells you that this is the canonical isomorphism from X to X dual. Anyway, the point is, of course, this theorem here, the Feynman types theorem. The graphical calculus that I just presented above is consistent, meaning two morphisms in a pivotal category are equal if and only if their diagrams are related by planar isotopy. And now it's just planar isotopy because you have cap and cap morphism. And this is really a nice, well, it's really a good, I mean, there's almost nothing to prove in some sense. Everything is built to work, but it's really a good statement. Like for pivotal categories, you have a two-dimensional graphical calculus, planar isotopies. And that's pretty cool. That's pretty cool. Okay, let me end. So this is absolutely great. Let me put well, 2 checks. It's really good. It's really good. So we finally have our two-dimensional calculus in kind of the best way you can imagine it. Like planar isotopies are basically determine whether two morphisms are the same or not. And it was this concept of duality because duality corresponds to having caps and caps. And my favorite diagram, which I always like to draw, is this one. Right? It's kind of the blueprint example, the prototypical example of a planar isotope. Okay, very good. I will end with something which generalizes traces. It's called a rigid, and it's pretty nice now. You will like it. I promise you will like it. So stay with me for the next 15 minutes or so, and then we're done. I call this generalized traces because it really, so rigid, pivotal, this was all a generalization of dualities in vector spaces. And yeah, you can generalize traces in vector space as well. And this is how it works. You take the skeleton of finite dimensional vector spaces. So this should be f finite dimensional ones, not vect, not so fd. And what is a pivotal structure? Well, it's the following. It's n. I mean, well, it's strict, so everything is double dual, and the evaluation map is the, what is it? The column vector of the standard basis things, and the co-evaluation map is the co-evaluation map is a row vector of the standard basis elements. And standard basis elements are just the standard base vectors 1 0 0 0 0 1 0 0 0 and so on of k to the n. Which secretly, of course, in this setup is just n, right? Strictly defined, just the object n. So all you need to do is to give a matrix. So if you have a matrix in from k to the n to k to the n, so aij, then if you do this calculation like a cup, so this is a cup. How do I do this? So this is a cup, and left and right do not matter, but let me just whatever. Let me just say this is whatever a cup. Orientations do not matter because everything is self-dual here anyway. And this is a cap. So you do a cap first. I will do an explicit example here in a second. You do a cap first. You do your matrix. You do a cap afterwards, and this is exactly the trace of the matrix. So this picture here, or this one, they're the same. This is just a trace of f. Trace f. Ooh. This is just trace f. And well, we do this really very explicitly. Just write it down on paper. You will see how it works. So if you have a matrix A, B, C, D, so n equals 2, and this whole calculation boils down to, well, I have my evaluation 2, which is the first thing I do. This is the co-evaluation. I swapped. I swapped everything around. So, and here's my evaluation. That's what I do last. Um, oh yeah, so everything is swapped in this example. I'm sorry. Anyway, so it's basically this calculation on vectors. Yeah. So here are my two basis vectors. Oops, I've put them into a bigger vector. I'm getting a bit tired. I'm sorry for that. And all you do is this matrix calculation, and you end up with a plus d, which is exactly the trace, which is exactly this picture in matrices. And of course, if you now put the identity morphism, then this picture represents a dimension. So this is a dimension of n, which is k to the n, which is n. So this is secretly k to the n. Dimension. So dimension is a closed circle, and trace is a labeled circle. That's all what I'm saying in this example. So in vector spaces, dimension is a closed circle, and trace is a circle with a coupon. Okay, so why not generalize this? So in a pivotal category, well, you have to again be careful. There's a right trace and there's a left trace. So here's a right trace, so you close diagrams to the right. There's a left trace, so you close diagrams to the left. But these are exactly the endomorphisms of trivial to trivial, which are given by those diagrams, right? And these are called left and right traces of a morphism. So F is my morphism. And yeah, and you have left and right dimensions in the very same way. Left, maybe I should do it differently. Yes. So you have left, you have right dimension. And you have the left dimension. And if you look at this example, the left and right is the same. So what you should do is, hopefully we don't worry too much about left and right in general. So we should come up with a definition that kind of catches exactly what you need, namely left is equals right, and you call a category spherical if left and right traces, and thus also left and right dimensions, because left and right I can't draw anymore. I'm getting tired. I'm sorry. Okay. There's another way of doing it, of course. So you call it spherical if left and right traces agree, which means left and right dimensions agree, because dimensions are just the traces for the identity morphism. And the reason why it's called spherical is, yeah. So here we had planar isotopies. So isotopies in a plane. And if you're in a plane, you can't do this move. You just can't pull this string and pull it all the way around because it's plane. But on a sphere, you can do this. You can take this string and pull it all the way around the sphere, right? And you end up with the other one. And this equality here is just saying that actually your diagrams secretly live on a sphere. So a spherical category is nothing else than the pivotal category where diagrams live on a sphere. That's what it is. And it's kind of a lesser move. So that's why I call it a lesser move, right? You go around yourself. And of course, things generalize as you think they are in vector spaces. This is just the examples. This is just what it is. In my favorite kind of little bit like Tory example, G-graded vector spaces. dimensions are always trivial. And in topology, for now, dimension is just a circle object. We will get kind of rid of this a little bit strange definition in a second. Well, not in a second, later, because for those diagram categories, this is endomorphisms of the trivial objects. They're pretty big. They're all kind of diagrams you can draw, uh, like this one. Um, the, while here they're really small, endomorphisms are just the ground field. Here they're very big. Any kind of circle diagram works. So the dimension itself, in this case, is just a circle, which is a bit silly because the dimension should kind of be a numerical invariant. So we may have to rethink this example later on, but for now, it's just what it is. So just keep in mind that we may have to rethink this. And as a warning, and then we are done. Being spherical or not actually depends on the choice. Namely, you have to be careful with the evaluations and co-evaluations. Remember that pivotal structure basically depended on a choice. Being spherical or not also depends on choice. And here I give you an explicit example for G being Z mod 3, so one bigger than my usual example. And the reason why I want it to be one bigger, because I want to take a complex, a third root of unity. So the 3 here is the third root of unity. And I can have duality maps indexed by the potential powers of this guy. And I can scale my evaluations and co-evaluations by third roots of unities. And if I do it for Z2, then kind of everything miraculously works out. But for Z3, so for third roots of unities and onwards, for bigger roots of unities, like seventh root of unities, you can play the same game. You would see that depending on your choice of the structure, actually, you could see that left and right traces do not need to agree. One of them is sigma squared, the other one is sigma. Sigma? One of them is chi squared, the other one is chi. So which means with this choice, it's pivotal. That's easy to check. Why? Well, let's look at this one. Well, if you do it this way, it's kind of scaled like that. You have a D and a D inverse, right? So they scale out and you still get this, but it's not spherical. And the point is, in order to be spherical, you put this one together with this one, and then you can't scale them out anymore, basically. You put this one together with, oh, this was bad. You put this one together with this one, and you can't scale things out anymore. Okay. So this was it means. So spherical is a choice. It's a bit annoying, but spherical is a choice. In most cases, as usual, it doesn't matter, and there's kind of a canonical choice. But at least for this Z mod 3 example, it's off by a root of unity. It's off by a scalar, and that's usually what happens. Like pivotal spherical structures might be off by scalars. Be careful with those scalars. It's not too bad, but anyway, the thing I want you to keep in mind is this order. So spherical implies pivotal implies rigid. So rigid is you allow left and right duals all over the place. Pivotal means left and right duals are the same, and spherical even means basically left and right evaluations of diagrams, like left and right traces are the same. The converse is not true. So this, for example, is a pivotal but not a spherical category. So the converse is not true. There's a hierarchy. So spherical implies pivotal implies rigid, but not the other way around. Okay, and you can prove, and all proofs are diagrammatic in nature. So please read them, but you can prove some easy facts about traces and dimensions and whatever. It's not so hard. Like the dimension of the unit object is actually the identity, so it's one. Everything is linear, so traces are linear, traces are cyclic. Yeah, I mean, they're very easy to show. Here is the, for instance, one of the proofs. You basically pull things around, right? Pull it around, and you see that it's cyclic. You change the order of F and G. So F, G, and F, G, F, and F, G. So you change the order by pulling things around. Really nice. Have a look at it in the notes. As usual, I link the notes below, right? But I'm running out of time, so let me just skip over it. Really, really easy. Proofs diagrammatic in nature, and you could play a little bit more with it. And kind of the point will be that rigid functors. It's kind of the point I will really like to make here is that rigid functors preserve traces and dimensions. So it's kind of the right notion between pivotal categories is if they are equivalent as rigid categories. So I say categories are equivalent as pivotal categories if they are equivalent as rigid categories, which implies that traces and dimensions are preserved. It's kind of the extra kind of information you have in pivotal categories. You better want them to be preserved. And yeah, I mean, sure, there are certain choices involved. So in ZMod 2, you can cook up choices such that you have two pivotal structures basically on ZMod 2. One of them gives you dimensions being 1. This is this one, choice 1. One of them gives you dimensions being -1. And they can't be equivalent as pivotal categories because equivalence of pivotal categories preserves dimensions. It's all this that I'm always trying to a little bit hide under the rug, but everything is kind of only kind of defined up to certain choices. Like pivotal involves certain choices. A pivotal itself doesn't involve certain choices, but the right notion would involve choices of co-evaluations and evaluation factors, and equivalence of pivotal categories would like to preserve dimensions of objects, say. So you have to be a little bit careful by well, you can basically choose scalars on the level of morphisms for co-evaluations and evaluations. This is what are almost the last two statements, or these are the last two statements, and I will come back to this later because because it's really cool. But for now, so in a braided setup, this will be this next time braided setup. This will be extremely amazing. For now, just we have the following statement about algebra objects. Remember algebra objects from last time. So, and of course, you have co-algebras. If you have a module, then the right dual has a structure of a left module. So if you have a right module, and then the right dual has a structure of a left module. Very complicated to remember. You'll see it in pictures in a second. The left dual has a structure, and if you have a left module, then the left dual has a structure of a right module. And the only thing you need to do is you need to use your evaluations and co-evaluations to turn say a left action into a right action. So this is a right action. Right? Remember, a left action was from the left, and right action was from the right. And all I'm doing here is I'm saying I can basically turn them around from left to right by using dualities. Right? Now this secretly comes from the other side, like this. So I turn the left action into a right action as long as I have dualities. So dualities swap left and right. That's all I'm saying, and this works for module categories as well. Yes, and that's basically what I want to say. This last proposition is just saying that if you have if you're in a pivotal category, so we have left and right duals, then the dual of a module of an algebra is a left and a right, in the right A module always. Um, which is a very nice statement. So you kind of also don't have to worry about left and right duals for left and right for modules of algebras. Okay, and that's basically it for today. So let me summarize. Was a pretty long one today, though, because so there is this notion of all we wanted was a diagrammatic calculus, which is kind of defined up to planar isotopies. And the right way of doing it is generalizing duality in vector spaces to what is called a rigid category. That's the one where you worry about the difference between left and right things. A pivotal category, this is the one where left and right are the same, and this is the one with a nice graphical calculus. And there's a spherical category, which is now even graphical calculus on a sphere instead of on a plane. Yeah, so today we just beefed up uh, the monoidal, the Feynman diagrams for monoidal categories to really good diagrams, which now live really on a plane or in a spherical setup, even on a sphere, and everything is defined up to the standard notion of well, to exactly what you want, to the notion of everything being equivalent up to planar isotopies. Okay, and next time we'll do even better. We will kind of put everything into three space, and this is what will be called well, a braiding, right? So you can put everything into three space. But yeah, thanks for watching. I hope this was reasonably helpful, and I hope to see you next time. Bye.